So my name is Gor Nishanov. I'm a developer in Visual C++ team. And one of the things I work on is design and standardization of C++ coroutines. Most efficient, most scalable, most open coroutines of any programming language in existence. And how many people attended any of the coroutine talks? We have about, okay, let's do it the other way around. So we had probably, I think every CppCon there is 1 or 2 coroutine talks. Who haven't been to any of them? Oops. OK. So this will not be an introduction to a coroutine. I put a few slides to give a context, but this still assumes that you are roughly aware how C++ coroutines work. But don't worry, we'll have a few slides to get you up to speed. So coroutines is a very, very old abstraction. It is a better function. It was invented 60 years ago by Melvin Conway. And Knuth gave it a more convenient definition as, actually, he did the opposite. He said that the subroutine is a special case of a more general construct, which is a coroutine. And if we look at it, coroutines are just like functions, but better, because they get 2 more operations. Just like normal functions, which get call and return, coroutines get 2 more, suspend and resume. And in C++, we are roughly getting this, or at least in terms of the Coroutine TS, which is currently going through the standardization process. So coroutine is a function which has an await, or yield expression, or a special form of a co-return statement. And one of the common patterns people use with coroutines are generators. You can think of them as a lazily produced sequence. So in this case, I have a hello generator, which yields character 1 at a time. And generator, from the perspective of the consumer, is just an iterable. It has begin and end. You can pass it to a range base 4. You can pass it to a standard algorithm. And what happens is that when coroutine gets to a suspend point, in this case it's yield, which pushes the value out of the coroutine, it gets suspended, keeping all of its state intact. And then when the main, in this case, will pull the next value, we will jump back in right where the yield was and keep going. Another common pattern with coroutines are asynchronous tasks. In this case, we have some activity which has an operation, an expression, which is not ready yet. It could be some lengthy operation, like, for example, TCP connection, establishing TCP connection, or maybe reading from a socket. And instead of blocking the thread, we will suspend the coroutine while waiting for the result of that operation to become available. And once available, coroutine will be resumed from the point where it was suspended, and will keep going. And many languages, about 11 by my last count, have acquired coroutines of roughly the same shape over the last 4 years. 10 or 11, counting the ones which are still in the design phases and those which already ship the standard with that language. It's Dart, JavaScript, C#, F#, Python. I think now Rust is in progress of getting them. Swift is getting in progress. So anyway, a lot of languages are getting those facilities. What makes C++ coroutines unique is the design principles that we established that wanted to guide the design of our coroutines. So we wanted coroutines to be scalable. Not like, hey, we will solve 10K problem. If you look it up, there was this problem. I think it's mostly Unix related. It's how many, can you handle 10,000 connections on the same box without creating too many threads? No, we're talking billions of coroutines. So the overhead of every individual coroutine is tiny. It's just a few bytes. So if you want to, you can scale to billions. So far, I have not seen a very good example of an application which uses billion coroutines, but we can hope. Now, coroutines need to be efficient. So the overhead of suspend and resume is equivalent or roughly in the same order as function call. And that actually gives a hint, or at least small hint to you what this talk will be about, because nano-coroutines are playing off from the fact that the switch between coroutines is less than 1 nanosecond. And we can do very funny things if that is the case. We did not want to do any funny business with stack switching, changing TLS that, for example, fibers do, that put any limit on what you can do inside of the coroutine. Moreover, coroutines themselves can be passed through a C boundary, through a ABI boundary, as a void star. And then from your third-party library, from an OS call, in a callback, you can reconstitute the coroutine back and resume it. And that allows very nice interactions with legacy C code. Finally, unlike most of the other languages which have coroutines, we did not tie coroutines to any particular runtime, because requirements for the runtime, say in the kernel mode or in embedded systems, could be very different from requirements needed for, say, UI applications or some others. So we made coroutine open-ended. You can define the meaning to them. We just provide efficient chirping up a function into a nice state machine. And finally, we added efficient cancellation to coroutines. So any coroutine can be canceled at any suspend point without relying on exceptions. And that is mostly to increase applicability of coroutines. There are environments like Google, for example, that does not use exceptions, or at least in a large part of your code base. And well, you can use coroutines there. Same with kernel, like in Windows, kernel exceptions are generally banned or actually unusable because runtime does not support them. Anyway, so this is what distinguishes coroutines in C++ from coroutines in any other language. And a couple of years ago, we went through a detailed talk where I explained what compiler does with coroutines, how compiler synthesizes the coroutines. And we saw what magic compiler is doing to turn all of those wonderful coroutines on the left into a tiny single constant on the right. So here you can see that we created a bunch of generator coroutines, then we compose them together, we pass them on to a standard accumulate, and in the end, we got a single number. Wonderful. So coroutines are very efficient and optimizable in C++. Last year, we looked at interactions between the networking TS and coroutines. So we can take this wonderful server, which is a little bit hard to read, and this is the same server, but written as a coroutine, which is the same efficiency, but easier on your eyes. So nano-coroutines. This is an application of coroutines in the field of databases. And I have not actually discovered that. All of the credit goes to researchers that presented and discovered that in VLDB conferences and written those papers. So why database people? Why people that goes to VLDB conference, which is very large database conference, care about coroutines? Especially nano-coroutines, coroutines that can switch in nanoseconds. Well, the trouble is very large database, a lot, right? And this is a tiny, tiny CPU. Actually, well, yes, it's a 4-core CPU on my laptop on which I was running the benchmark. Look at those tiny, tiny numbers. L1 cache, 32 kilobytes. L2 cache, 256. L3 cache, 8 megabytes. And then memory. And it takes 16 nanoseconds to bring a value from the memory to the CPU. And because it's a very large database, their indexes, they're gigabytes. They're all in memory. And they're hit at random spots. So whatever you do, whatever wonderful cache locality you're trying to achieve, when you start hitting those indexes, you're hitting memory in absolutely random spots, and nothing can help you. So let's see what happens. And I will use the simplest algorithm we can have for index searching, a binary search, because it fits the screen. Databases use more complicated bit trees and hashing and combination of those, but this will be good enough for us. So it is a version of the binary search, mostly stolen from a lower bound, with one extra check which allows us to bail out and earlier than the standard algorithm. So let's run it on a small array. Wonderful. If it fits L1, we're getting roughly 4 nanoseconds per lookup over log 2. In this case, I have this little metric which allows us to evaluate how good the algorithm performs by simply dividing how long did it take to look this, to do the search, divided by the log of the size of the array, which is roughly how many hits into the memory it will do. So wonderful. Array comfortably fits L1. We are barely having any misses, 4 nanoseconds per lookup. OK, let's grow bigger. OK, 4.7 nanoseconds. Reasonable. Well, half of the L1 cache misses, but L2, if you see, is just 3.5 nanoseconds latency. So still not bad. Again, even when the array fits L3, still wonderful. Now, this is where we're getting with databases. With databases, the actual index is gigabytes. So even with this tiny array of 256 megabytes, suddenly we're having 0.21 instructions per cycle. This CPU can do 4 instructions per cycle. Here, we're doing it the opposite. It's like 1/5 of the CPU speed. And what can you do about it? Like people have those wonderful data structures trying to do cache optimizations. But what if your memory access pattern is horribly random? Well, if you want to do only one lookup, nothing can help you. Nothing can help you. But luckily, in databases, there is this wonderful join operation, which does a lot of lookups. For example, here we have 3 tables containing some customer orders, customer names, and what food customers are eating. And now we're doing the join operation. So probably database would go through one table in a nice linear fashion that will have wonderful cache performance. It will go one by one. There will be prefetching of big pages, so it will nicely go through all of them. But then when it has to use the foreign key to hit other table, oops, it's random. It's random. The core will be very, very sad. It will do just a little bit of work, and then 60 nanoseconds of nothing. Now, 60 nanoseconds is small enough so that it is not worth to switch into a different thread, because switch to a different thread is what, half a microsecond or more? So it's much bigger. So core is being wasted. Of course, there is hyper-threading. But normally on CPUs, how many hyper-threads are? 2. 2, right? 2. OK. So core will be slightly more happy, because what it will do, it will run until it hits the stall, memory stall. Then it will start running the next thread. But if it hits the stall, again, we're stuck. So what can we do to make it better? Luckily, CPU hardware vendors provided us with prefetch instructions. And this is an intrinsic with a bunch of hints, which allows us to tell to a CPU, hey, CPU, we're interested in that memory location. And we can give it a bunch of hints. For example, if I say hint T0, it means I actually want that value to be fetched from memory and then go into L3, L2, L1, because I want it to be all throughout. And NTA, the last option, It's actually the least disturbing flavor of prefetch. It's where I have important data in my caches, and I don't want to evict it. Instead, I want to prefetch the value from that memory location as close to CPU as I want, as possible, without trying to disturb other levels of caching. So this is what we will be trying to do. We will try to do instruction stream interleaving. Because our join operation needs to do multiple lookups, we will try to do something like that. We will start the first search, and then at the point where our binary search used to just read the value from memory, we will issue a prefetch instruction, and then switch to a different search that we still need to do, because the join operation requires multiple lookups. And then let it run until we hit a memory read from a random location. We will issue a prefetch, switch to the next one. And then when we have enough of those, hopefully by the time when we did the last one, the first one we prefetched is already in memory. Sorry, it's already near the CPU, so we can switch to the original one. So essentially what we'll be doing hyper-threading in software. OK, it's actually not that hard. It's just you have to be very, very meticulous about how you're going to do it. So this red line shows roughly how we're going to split that function and try to turn it into a state machine. So here we'll have this star middle that is trying to read from memory. And we'll just partition it. Well, since we need to make it a state machine, we first need to extract all of the state we need that currently inside of that function. So do we need first? Yeah, we need it because it is used both before the red line and after red line. Same with last, middle, length, half, value, the value that we are keep comparing. OK, and we need a state. And we need a state so that we know which part of the algorithm we are before the read or afterwards. And we will add, and we will run that state machine with just two functions. Initial one, which executes the first time we enter the function and until we hit the read or prefetch instruction. And then the one that will run the rest of the loop. But again, we will split it up so that we stop just before trying to read from the middle, issue a prefetch instruction, and then get out. So very straightforward. This is the initial entry. We copied all of the values that were before the while loop. Then, well, if the range is empty, we will bail out, and we will mark the state as not found. Otherwise, we will do all of the stuff which happens before the read, namely half divided by, sorry, we divided the length stored in half, computed the middle, say that we need to keep going, and we issued the prefetch instruction I showed earlier. Great. Now, run will do the rest of what happens once we read. So now, the value, we think that value have been prefetched. So now it is safe to say star middle. So we got the middle key, we compare it. Is it on this side? Is it on that side? We did the early bailout. And one difference here is that before, in our binary search, bool or the return value was indicating whether we found the value or not. Here, I'm using the return value of run to simply indicate, do we need to run it more, or we're done. And the state that will be storing found or not found will be the thing that will be telling us whether we found a value or not. And then we will prefetch the value again. And now, yeah, I think we covered all of it. And we'll mark the state as not found. It's tedious, but doable, right? OK, I see one hand. OK, good, good. Sorry, one head nodding. So, and we want to run it roughly like this. We will create a bunch of those state machines, and then we'll say, run init on this one, so it'll initialize this frame, hit the prefetch, then do the same for the second frame, and keep going. Now we initiated n prefetches. We go back and call run. We hope that by the time we get back to the first one, prefetch has already completed. So we will run it again until we hit the prefetch, go to the next one, and say this one either found a value or reached the end of the algorithm. So we're done. So we consume the result in whatever fashion the database wants, and replace that frame by running init now for search number n+1. And we will keep going. I will bore you with roughly showing the code, how it looks like. Something like that. We create a vector of frames. We go through the list of all of the lookups we need to do. And then if the state in a particular frame is not equal keep running, we will initialize it. Otherwise, we will call run until it's either found or not found. If in either of those cases, we'll initialize it again, and so forth, so on. And in the very end, we need to deal with stragglers. What it means is that we run through entire list of lookups we need to do. But we still have frames that have searches that haven't completed yet. So there will be a tiny loop at the end that will take care of those. OK, let's see how we did. So with naive search, we were getting 26 nanoseconds per lookup over the log of an array size. Now, we're getting something. We just make it 2.5 times faster. And that is with interleaving with 16 streams. Essentially, I ran it with different amount of frames and until I find the number of frames which is sufficient for us to do enough work between the prefetches so that by the time we go to the first one, it's already there. But it's nice. But that's a lot of code. Moreover, we did a very, very simple algorithm, binary search. Now imagine we want to apply that technique to more complicated algorithm. That is not manageable. Can we do it better? Yes, we can. And we can do it with coroutines. So at the very beginning, we talked about two common patterns people use with coroutines. One was generators, lazily produced sequences. Another, async tasks that await for some asynchronous I/O completions. So which of those two kind of problems this problem reminds you of? Who thinks it's generators? 2. Who thinks it's async tasks? A lot. And you are right. And you are right. Moreover, that coroutine-based TCP server we looked at last year is actually showing us almost exactly the kind of patterns we are going to use to deal with this problem. Because the top part, which is a session where we waiting for TCP read, and then once read completed, we do a write, and then read again, write again. It has the property that this coroutine doesn't go anywhere while we're awaiting for the result. And that is roughly what binary search is doing. Because binary search, you can think about it, a read from memory. Oh, that's an I/O. That is an I/O that takes a lot of time, 60 nanoseconds. With our coroutine so fast, 1 nanosecond or less switching, we can do a lot. And one change before I switch to a coroutine, I will change the way how we deal with the result. So here we return the result as a Boolean. I want to return the result as in the form of a function object. And if you notice, Alex Stepanov, a long time ago, discovered that this callback kind are the best kind. If you have a function object, compiler can actually inline it inside of the algorithm, and it will be very, very, very efficient. So that's why we're doing it this way. And you know where I'm going to with it, because this is it. This is how long will it take us to convert the algorithm from a plain one into a coroutine. Essentially, we have some kind of coroutine type. We change void into a coroutine type, and then we replace the plain read into a waiting on a prefetch operation that will suspend the coroutine while value is being prefetched, and then hopefully resume it at the right time when the value is already in memory. And yes, we need to replace return with Coroutines. There was a battle 2 years ago, and the Coroutines have won. So we need to write Coroutines and coroutines. OK, so that took care of the algorithm. Now we need to write an orchestrator. Let's get back to our TCP-based server. So the bottom part actually has the pattern we want, because unlike the session, which gets suspended while waiting for the result of the read or write, we don't want a server to be suspended while waiting for a particular session to work. We actually would like to spawn as many sessions as we want, and we want them to live independently from the server itself. And in this case, because having detached activity running wild, like detached thread, is horrible, never, never, never do it. Here, we're actually associating the coroutine with an I/O context. So in networking TS, I/O context is the thing which tracks all of the activity which is currently in flight. So in this case, we're spawning, and we'll make the coroutine independent of a server, but still there is a way to join them in the end or cancel at the shutdown. And that brings me to roughly this shape of an orchestrator. So here, instead of I/O context, we will have a throttler, because we're potentially doing 1 million lookups. We don't really want to launch 1 million coroutines. So the throttler will just have enough coroutines to keep the prefetcher pipeline busy. So, and this multi-lookup gets the concurrency parameter, we're giving it to a throttler, and then throttler will spawn enough coroutines to keep it busy, and in the end, we will do the join. So another name for this pattern is fork join. You probably have seen it in CBB and others, because what we're trying to do is to spawn a whole bunch of stuff, and then in the end, we want to wait until all of it is done. So this is how we imagine the simplest possible way to solve this problem. Does it look simple to you? Yeah, because it's very close to what we're doing first with TCP server, and second, the algorithm itself is almost the same as a naive version. So now let's see how much will it take us to actually make it work. And that is actually quite a good approach. Frequently, I advise when people say, hey, how can I do this with coroutines? I will say, well, first, think of the best way of solving this problem. Just imagine the syntax, and then you can make it work. So that's roughly what we were doing here. We thought of a way how would we write it in an ideal way, and then figure out a way to make it with coroutines. So the first part, we need to make prefetch unawaitable. And a quick reminder for those who haven't seen the other coroutine talks, awaitable is a thing with 3 functions: await ready, await suspend, and await resume. So compiler expanded into something like that. First, it asks, hey, you, awaitable expression, are you ready? And if it's ready, then it proceeds straight to the end into await resume, which unpacks the result. And the result of entire await expression is whatever await resume have returned. Now, if it's not ready, then compiler calls await suspend and give it as a parameter a handle to a coroutine it manufactured. And the handler for await suspend can then do something with it so that it can resume or destroy the coroutine later when it knows the result is available, or if it knows that we have to cancel and get rid of all of this stuff. So let's do the awaitable for prefetch. So we're going to try to implement this prefetch awaitable templatized on T. So first, we need to remember to grab a reference to the value. Right, so whatever is passed in the constructor, we will just store a reference. Reference is cheap, right? It's just an address. We're not reading anything. Now, at the very end, when our await is satisfied, we will just return that reference to whomever, and hopefully he will actually use it for good, namely to the reference and get the value that we were looking for. Now, in this case, if you look at the prefetch instruction, it doesn't tell us whether the value is already in the cache. Moreover, probably that will not be a very good instruction because it will take a while for hardware to figure out whether it's in the cache or not. We want to be very fast. We want to cycle a lot of coroutines. So we'll just say, nope, prefetch is never ready. We assume that it is always in memory. So we need to go on a suspend path. And in a suspend path, it's quite simple, actually. We will call that intrinsic that I showed earlier, give it an address of a memory location that we want to prefetch. And in this case, I gave it a hint because I didn't want to pollute any other caches. I want to just, we hit at random spots. Every time will be different. Give us straight to the CPU. And now I want to put this coroutine. You see, there is a coroutine handle that was passed to await suspend. And I will put it into some queue that will put it at the very end of the queue. Now, a couple of years ago, when we were talking about different coroutine flavors, we talked about symmetric and asymmetric coroutines. So asymmetric coroutines, they support only suspend and resume operation. So in order for, well, when you suspend, you return back to the caller. And resume is a different operation that will resume you. So there is this unequal relationship between the guy who called you and the coroutine that suspended. There is also a symmetric coroutine variety, which allows direct coroutine to coroutine transfer, more like thread-to-thread context switch. And even though functionally those kind of coroutines are equivalent because we can convert easily one into another, there is a cost of conversion asymmetric coroutine into a symmetric one. And I actually observe that cost right here because we're talking nanoseconds. This was my first implementation where I simply added a coroutine handle to this queue, and then I return control back to the scheduler, which runs the loop, which dequeues now the coroutine from the front and resumes it. Well, that's about 3 cycles. And 3 cycles is about 0.75 nanoseconds on that machine. And we want to pack as many coroutines as we want. And I wanted to eliminate that. Luckily, we have a provision in Coroutines TS which allows symmetric coroutine to coroutine transfer. So what we want to do here is this. That way, we essentially eliminated the scheduler. Scheduler became just a very, very simple dumb queue. We're saying, put ourselves at the very end of the queue. Get the coroutine at the front of the queue. And that is the coroutine I want to symmetrically transfer control to. So this becomes simple jump from this point to a different coroutine. OK, so queue is boring. It's anybody can write it. Yeah, and at the very end is just try pop and a run that will keep trying popping the coroutines until there is no coroutines anymore. And resume on the coroutine handle is the thing you use to resume the coroutine which is suspended. Any question on the queue? No, that's... OK. Let's see. What else is left to implement? OK, now we need to implement a throttler. Let's look at the binary search again. I lied. I said it's a task void. And task void is something which currently goes through standardization process. It's a zero overhead feature. We talked about it 2 years ago in the coroutine under the covers talk. Well, this is not it. I'm going to hack it a little bit. So it will be a root task, because I want a root task to be aware of the throttler. And it's a yucky part. I will show how to fix it later, but I need this, so my apologies in advance. So what throttler needs to know is, well, what is the concurrency factor? How many coroutines it wants to keep concurrently? And in the spawn, it will check. If it populated the queue with enough coroutines, it will start running them. So essentially, here what we're doing, we'll pop in the first coroutine from the queue and resume it. And then it will start jumping around from coroutine to coroutine, because we saw the await, right? Await for prefetch is actually doing all of the scheduling, and it'll keep running until one of the coroutines run to completion. And that will create a room in the queue. That's why if the limit is 0, I will start running the first coroutine, and it will run everything else. Otherwise, I will associate this coroutine with this throttler so that it knows to tell me when it's done, so that I can bump up the limit, push it into the queue, and decrement the limit. And on task done, it is the callback that essentially the coroutine will call at the end that will increment the limit. And the rest are boring functions. So I needed to do a few tweaks to the zero overhead feature. And this actually shows those tweaks. First, I needed to add set owner, which will disassociate the coroutine from this array type, which is going to destroy the coroutine and its destructor, and transfer the ownership to the throttler, because now this will be the guy who will be running the coroutines and will be destroying them in the end. And I will remember the throttler in the promise type, and I change my final suspend from suspend always to suspend never, which means the coroutine will self-destroy itself in the end and will let know the owner that the task is done, so it reached completion. Finally, because I'm creating a million of coroutines, million potentially coroutines, I will use a recycling allocator. So if you overwrite an operator new and delete on the coroutine promise, you can supply your own allocator. And that helps a little bit, extra few nanoseconds. And again, every nanosecond counts when we're doing this kind of operation. So let's see what happened. So we have 26 nanoseconds for a naive version. We have 10 nanoseconds for a handcrafted version with 16 streams. And do you think it will be better or worse with coroutines? Yes, it's actually better. So we're getting to almost 3.5 time faster performance, and we have to have 20 streams to get it there. Oh, thank you. So you all have to leave early. We're almost at the end. So negative overhead abstraction again. So Alex Stepanov, when he was in one of his interviews, when he was asked how to design good abstractions, he explained that it's not like you invent abstractions from just your brain, from thin air. No, you start from a concrete problem. And then you look at the most efficient way to solve that problem you know today. OK, at that point, you can try to invent abstraction and now recode that problem using this new abstraction and see how much overhead have you introduced. If not, wonderful, you have a good abstraction. Try applying to some other pattern, and so far, so on. So what happened with coroutines, and this is not the first time, is that when we take the best possible pattern we do today, say with handcrafted state machine, and then recode them with coroutines, for some unknown reason, it becomes faster. So it is not just abstraction penalty, it's a negative overhead abstraction. And I tried to understand why it happened. So I was looking at disassembly, because pattern of access for both handcrafted state machine and the coroutine-based state machine, it is identical. I am running them on the same array with the same set of values to look up. One of them is faster. And I think it happens because of when coroutine transformation takes place. So both Microsoft compiler, Clang, and a GCC implementation, which is currently in progress, discovered that the most profitable way to do a coroutine is to actually let the coroutine be observed by a compiler as a normal function for as long as it can, so that optimizer can simplify the body, can do the constant propagation, can do the common expression elimination, like do all of the awesome stuff compilers do, inline things, discover after inlining that some other stuff disappears. And once you finish simplifying the body of the function, then you do the transformation of the coroutine into a state machine. So you chop it up into small pieces, and then you optimize the individual pieces. So what happened here, we humans, we did the transformation of a function into a state machine too early. We did it at this very high level before compiler had any chance of doing optimizations. And once a function is chopped up into pieces, it becomes a state machine. Compilers are not very good at optimizing state machines. So that is my guess why it's actually faster. If you look at disassembly, you will see that the handcrafted state machine puts too much register pressure on a compiler. It is too complicated code. It starts spilling and reloading values into the memory and into the registers. Whereas coroutines, after it's chopped up, it becomes very, very simple. It does almost the same thing that you would have done if you're trying to write this in assembly. So that's nano-coroutines for you. We're taking advantage of the fact that the switching from one coroutine to another is taking less than a nanosecond, and in some cases, 0 in case coroutine is inlined. Unlike, for example, fibers or stackful coroutines, which takes from 10 to 50 nanoseconds to switch depending on the OS architecture, CPU kind, and how many registers they have to save and restore when they do the context switch. And naturally, you cannot do that with threads, because there we're talking close to a microsecond switch. So this approach allows you to deal with memory latency in those cases where nothing can help you. No more packing of your data in a cache where data structures can help. Nothing. You hit the memory at random spots. Well, if you have more than one lookup, you can try to split your code into several streams and then use coroutines to interleave them. So, coroutines, current status. Proposal is going through the C++ standardization committee. Maybe it will be in C++ 20. We have implementations in Clang and Visual Studio. GCC implementation is in progress. Nathan, yes, well, yes, in progress. I see he is nodding there. No, he's leaving the room. Oh, no, he's coming here. Excellent. So I think we have a confirmation that GCC implementation is in progress. Last year, we had a talk where we talked about naked coroutines. And that was one of the complaints, that coroutines are just a compiler feature. You always have to come up with your own types to play with them. No longer naked. We have the task type going through standardization. We have the generator type that is supposed to come in San Diego, which is just in a few months, and a bunch of wonderful, wonderful, wonderful algorithms that work on awaitable types that will help too. And this is just a reminder. I'm told to put this slide, so there are other useful talk, and we're at the end of Wednesday, so I'll put it back again. So questions?
Yeah, so Gor, you're correct. We've started an implementation, so Facebook's hired a GCC engineer to work on this. It started a week and a half ago, so, but we have a design document that I've been working with Gor on and the like, so it's not from a standing start. If you go to the GCC wiki page, there's now a new project page where you can see what's happening, but it'll be a while before there's a result.
Wonderful. Do I need to repeat the question? Oh, excellent. Well, it's awesome. So I was not lying. GCC implementation is in progress. Even though it's only a week and a half, it's still awesome. It's still in progress.
So what's the performance of the coroutine implementation like without the allocator? And to what extent does that allocator rely on the fact that all of those stack frames are expected to be exactly the same size? I.e., if you were in a place where you couldn't rely on that, would the speed up be similar?
So I think it was about 10 nanoseconds. So if I was surprised how well malloc actually behaved. I didn't use tcalloc, I just used very dumb recycling allocator. But even without it, malloc was doing an amazing job. But I wouldn't recommend, because if you are going for nanoseconds, you better use some good recycling allocator.
Of course. All right, thanks.
For those of us who want to write applications that other people are going to run on a variety of machines that may have more cores or less cores or more cache or less cache, what facilities are there going to be to make the throttlers more well-behaved without hand-tuning them?
Well, with the current instruction sets as they exist today, right, that will not give you visibility of, say, how busy Prefetcher is, you have to tune it by hand. But I've been talking to some, I think, Intel engineers, what kind of other facilities we could have. For example, there could be, and again, this is speedballing, it's not real, nothing is happening, but potentially you can have an instruction that can tell you, hey, Prefetcher is that busy, and thus you know you need to feed more to it. And if it's completely busy, well, then you don't have to spawn anymore. It will not help you at all. So this kind of help. Another one somebody suggested was to have a prefetch instruction that will give you a hint whether the value is already somewhere close. But that is likely to be a more expensive instruction than a plain prefetch, because you'd have to go and check in a bunch of places.
I would even be happy to let the throttler or whatever initialize itself and run some kind of test once at the start of my program and then use that data, if that's another way that the library could go.
Absolutely.
Hi, I'm interested if my own data structures and algorithms are cache friendly. Can you comment on the profiling toolkit you use to show your latency?
I used perfstat. It's Linux tool perfstat to show me the Intel counters, the CPU counters.
Perstat, what was it called?
Perf space, yeah, perf.
Prostat, okay.
Perf, P-E-R-F, perf tool. It has a bunch of very useful primitives, and if you want to look in more details, I think Chandler had been given a couple of talks last CppCon, going nowhere faster And the previous one before that, he showed how to use perf tool to get the information about caches, about stalls, front-end stalls, back-end stalls. Perf stat is a wonderful thing. It also works as a profiler. You can say perf record and then perf report, and you will see wonderful text-based UI, which is pretty decent. And on Windows, you would use something like vtunes, but you have to, is it vtunes, right? Intel, but you have to pay. On Linux, it's cheap. It's nothing.
So this looks super awesome, but what if you put a breakpoint inside of a coroutine and look at the call stack in a debugger? Like, is it a nightmare?
Well, if you put a breakpoint into a coroutine, you will see roughly let me get to the, okay, hold on. Okay, anyway, it's too far to get to the code I want to show. But what it will show you, you will have your binary search outer function, right? And then that function calls resume, and that resume you will be in a coroutine. So you'll have just two functions on the stack. You will see a function, the multi lookup, and the next one will be a coroutine at that point where it is currently executed.
So there's not a bunch of like sort of impenetrable functions deep in some standard library in the call stack?
No. Every time you look, you will see a normal thread, and you will see the currently executing coroutine and what function invoked it. And in this example, it will be just the multi-lookup and then a coroutine where it's suspended. And if you want to see where other coroutines are, then you need to go and look at the queue, which has coroutine handles. And in Microsoft Debugger, we will actually tell you what function it points, at what suspend point it points. But we have plans both in MSVC and hopefully have extensions for other debuggers that will show you as if it's a call stack. So we'll show you here's a coroutine suspended here, and here's all of the locals it has at the moment. Right now, you cannot examine coroutine handle in this fashion unless it's a currently executing coroutine.
Gotcha. Thank you.
I'd like to know if there is anything to think about in terms of what the prefetch intrinsic does with regards to C++ memory model. Is there anything funky there with like acquire release semantics? Is it possible not to see the results of some memory operations done by some other thread?
Well, prefetch is just a hint, right? So the actual operation we are doing is dereference. That is where we will start worrying about the semantics. We will start trying to get that value from a cache or from memory. Prefetch is just a hint to a CPU, hey, try to get me a value. The real work will be done when, well, sorry, not real work, but at least the one that have all of that semantic associated, it is the actual dereference, read of the value.
So the memory access itself should be the subject of the same limitations as applies to any other program outside of coroutine case, like putting memory barriers and so on.
Actually, I think I replied incorrectly to your question, in the sense that yes, we need to make sure that the prefetch is not moved around the actual read operation, and I'm not sure whether it's hardware catching it or it is an intrinsic which is marked somehow in the back end, which prevents reordering.
And just another question. It sounds like execution TS is something that you don't really need to integrate with or care about because you're completely outside of the whatever threading model, execution model is going to be in C++. Because it seems to be like completely unrelated with anything threading, right?
Yes. Okay. Yes. So coroutines love executors. Coroutines love networking TS. Coroutines interact with other things, but by itself, they do not require those facilities. But if you want to interoperate with them, they can. And there is a paper in the, if you know where to find the standardization mailings, there is a paper of coroutine impact on library facilities. You bing this name, you will see how it's supposed to interact with executors, with networking, and other things.
Thanks. Hello. So in my day job, we use like a bunch of fiber managers to run on different threads and basically serve connections with clients. And there is kind of pain to use mutexes and statics because they kind of grab lock somewhere inside. And like, they basically block all the fibers on the same thread. Is it going to be the same with coroutines? Or you're going, because like for fibers, we use special fiber mutexes?
Okay, so one of the fundamental problems why you don't want to migrate fibers from one thread to another is related how thread local storage code is generated. So compiler is unaware of at what point of your function you can have the fiber switch. That will also switch the TLS. So if you go to Godbolt and compile some ARM code that uses TLS, you will observe that it will cache in some non-volatile registers the pages of TLSs. And thus you will be either reading garbage or corrupting the memory if the switch occurs. Coroutine control, like the stack class coroutine like this, suspension point is called out. It is observable by the compiler. So no TLS caching is performed. Now, if you are actively trying to defeat or write a bug, you can. But you can never get into a situation where you are using a facility like magic statics, or maybe thread caching allocator, or error underscore value, which is undercovers, uses the magic statics. You will not end up in the case where you will trash the memory or read garbage with these coroutines. So they are safe to migrate as long as you're not actively writing bugs.
I see one follow-up question. What about your like primitives of STL? Are they going to be like variants with which support coroutines?
Okay, so we have, at the moment, we don't have any asynchronous I/O in the standard. But there is a networking TS which is in flight, which might land in 20 or might land slightly later. So that networking TS will be interacting nicely with coroutines. And if you look at CppCon talk called Naked Coroutines Live from last CppCon, there will be a demonstration how you can hook up networking asynchronous I/O and coroutines.
I watched that. I'm speaking about like I/O streams, for example.
Well, I/O streams are not asynchronous yet. When there will be, we can start talking about coroutines.
As I understand, the time when we await the result from Prefetch depends on the size of schedule queue. So if it's enough feature to between the Prefetch and when CppCon move data to running cache, one cache, its algorithm will work best of worst. You compare two realizations, but in one case was 16 streams, and the other case 20 threads.
Yep.
You compare working this algorithm on same amount of streams.
Okay, so what happens is that the handcrafted state machine were doing more work. So therefore, I only can launch. It does more. It consumes more cycles in that little squiggly area here. Sorry. Okay. So this squiggly, where we actually do useful work between the stalls, it was doing more work. Therefore, I needed less of them to consume this empty space between the squigglets. Whereas with compiler-generated state machines that I did from Coroutines, it was actually using less instruction to do the same amount of work. So I was able to feed more coroutines to do more concurrency. But I determined that empirically. I just ran them with different concurrency numbers and saw which one gave the best performance.
Okay, thank you.
So I wasn't trying on purpose to make the handcrafted state machine worse. It was actually the fastest timing I got was with 16 of them.
Hi. Wanted to ask about the binary search. I'll try to make it quick. So in order to know what else you would need, wouldn't you need to do some redundant work and bring in some stuff you might... So to know which thing you're going to need next, you need to resolve the current check. So you need to sort of do work that you never would actually need, right?
Well,
so as in, and prefetch stuff that you wouldn't really require if you would just do it right, like this, linearly.
Well, this is exactly the sad situation because if you knew in advance that you need that, and that one, you can prefetch a whole bunch of them. But you can't. You first have to prefetch a value before you know where to go.
All right.
That is what makes this problem very sad problem, unless you do prefetching combined with instruction stream interleaving.
My point is that you're pulling more data into the memory, evacuating more stuff out of the memory than this thing, right? In some sense.
So in my testing, I've been using the Prefetch NTA, which is trying to move the value directly into L1 cache without touching L2 and 3. So supposedly, say, if you're a database, you have some real data you want to do work with, and index is just a way to get to the data. Right. So in this case, I'm trying to be very frugal and not evict stuff from big caches which have data and use Prefetch NTA.
Okay, one
avoid that.
Can you put the slide back with all the presentations?
Say again, which one?
The slide with all the presentation times. You had a slide that says all the other talks.
Sorry.
The second to last.
This one?
Nope, the last.
The last one.
The end.
Hold on, I think I know the faster way to get there. This one?
I wonder if, to clarify the question from before, you weren't optimizing a single search to be faster. You were optimizing many searches to happen in a less amount of time. So it wasn't the single search that he was prefetching. He was just interleaving many other searches.
Oh, yeah. Thank you for clarification. Yeah. If you have to do only one search, nothing can help you. And that is why database people are interested, because they actually do multiple lookups.
Would it be also possible to optimize single search if you stop prefetching sooner? Because, well, every time you access memory, you are actually pulling a little bit more data into cache, right? So, like, let's say when you are making less steps in binary search, and when you're observing, like, last, I don't know, 4 values or something like that, so you probably don't need to do it in separate steps.
Can you speak slightly closer to the microphone? For some reason, I'm not getting it here.
Oh, sure. So my question was, when you prefetch something from memory, so CPU is not pulling single byte, right? So it's pulling a couple more bytes after that into cache. So probably you could stop prefetching for the last couple iterations of the binary search. And by doing that, so probably you would speed up a little bit individual search.
Possibly. I will put up the code on the GitHub and have fun, party on it, see if you can make it faster. Okay, thank you very much.